Hello everyone, this is Physics 11, Chapter 6, Thermal Energy and Society. Now, everyone is aware of what comes out of a volcano. Lava reaches a temperature over 1,000 degrees Celsius and can burn everything in its way. Now, where this energy comes from? The core of the Earth, 6,000 kilometers deep, is very hot, 6,000 degrees Celsius. So that enormous amount of energy, it is very crucial for us to survive on Earth. And for more, it is a very useful type of energy that we call geothermal energy. Scientists are working hard to figure out the best technologies to harvest this type of enormous amount of energy. Here are some key concepts that we're going to learn this chapter. We'll be able to describe the differences among temperature, thermal energy, and heat. We'll solve problems involving quantity of heat and apply concept to the situation involving heat exchange. Explain the temperature change involving the state change, and mathematically determine the energy involved. And we'll describe the impact of heating and cooling system in society and in the environment. Section 6.1 is Introduction to Warmth and Coldness. There was a wrong perception of the warmth and coldness. During the 18th century, scientists thought that warmth and coldness were produced by a constant universal massless fluid called caloric, which flows naturally from warmer object to a colder object. They thought that material could become only hot if they are in contact with even hotter material that could transfer that caloric to them. They were wrong about that constant universal massless fluid. However, they were not wrong that direction of the heat from hot to a cold object. Benjamin Thompson was the first one that shows in his investigation that caloric did not even exist. Warmth and coldness are produced by vibration of atoms and molecules. The kinetic molecular theory came to life. So what it says, the kinetic molecular theory is based on idea that matter is composed of the particles, atoms and molecules that attract each other and have a certain amount of kinetic energy. So it is a kinetic energy that causes the particles to be in a state of constant motion, vibration. So the bigger the kinetic energy, the bigger the vibration. And I want to make sure that you understand that kinetic energy is internal kinetic energy of the particles, not that kinetic energy that we are used to learn about mechanic energy. Previously, we learned about matter, and matter is everything that has mass and take up space. Matter exists in the form of solids, liquids, and gases, three states of matter. In solid, particles are held in a fixed position by forces of attraction between them and vibrate because of the kinetic energy they possess. So those particles are held in a fixed position because they do not have enough kinetic energy so they can move around. However, according to kinetic molecular theory, an increase of motion of the particles, the substance will feel warmer, and decrease in motion will make that substance feel colder. So there is a connection between how they move, those particles vibrate, how much they vibrate, with how the matter feels, how that solid feels, warmer or colder. Let's look at vibration in liquids. In liquids, particles have more kinetic energy than those in solid. So that causes the particles to vibrate even more rapidly. Also, they are free to move from one place to another. However, they are still together in layers. That will give the ability to flow. That will give liquids ability to flow, and those layers can easily slide on top of each other, so liquid can take the shape of the container. Now, there's a misconception about solids like powder. When you see the powder in a jar, you might think that powder can take the shape of the container. Like liquid, if the solid is very tiny, has a very tiny particles, they will take the shape of the container. Now, to prove that wrong as a theory, as a misconception, you can try two different things. You can take a liquid which has a high viscosity, like oil or even honey, and compare that with powder or sugar. You can make a pile out of sugar, but you cannot make a pile out of honey or oil, because eventually those layers are going to slide on top of each other and is going to have that horizontal level. So that's why we use liquid to build a device to show how horizontal the surface is, which is called level. And we cannot use that with a powder or a sugar or any solid, no matter how small those particles are. So liquids have ability to flow, and liquid can take the shape of the container. Gases are different. The particles of gas have more kinetic energy of those of liquids and much more kinetic energy than particles in solids. So this causes them to vibrate and move further, much further and rapidly from each other. So that's why the particles in a gas can fill up the container, because they are free to move everywhere. Compared to liquid, which particles of liquids can take the shape of the container, but they cannot fill the container, cannot fill up the container. Gases can. So you can have a half glass of water, but you cannot have half container of gas. So gas, although might have higher pressure or lower pressure, more particles or less particles, but those particles are evenly spread and fill up the container. Particles of matter possess many forms of kinetic and potential energy. And kinetic energy is associated with a motion, kinetic motion. Motion of the atoms and molecules, so motion of the particles of the matter. While the potential energy is associated with a force of attraction between these particles. The total amount of kinetic and potential energy possessed by particles of the substance is called thermal energy. So it's a total amount of kinetic and potential energy possessed by all particles of the substance. When we talk about energy, we talk about transfer of energy and transform of energy from one form to another. Thermal energy can be transferred from a warmer object to a colder object only. One-way transfer. The thermal energy of the object can also be transformed into another form of energy, like any other type of energy. How can we measure the amount of thermal energy on object? It is impossible to measure the kinetic energy and the potential energy of every particles within an object. However, we can measure the average kinetic energy of the particles. There's a closer relationship between temperature and kinetic energy. Temperature is a measure of average kinetic energy of the particles in substance. Average, not kinetic energy of the particles, because it's impossible to measure kinetic energy of each individual particles. Even more, we can say for sure that at a particular temperature, some particles may even move faster than the other. But one thing is true. The majority of the particles of the warmer object move faster than majority of particles of a colder object. So we can say the temperature of the warmer object is higher than temperature of the colder object because the warmer particles possess more kinetic energy than particles of the colder object. Temperature is average amount of internal kinetic energy of the moving particles in a substance. Now, how can we measure that? Temperature is often measured using a mercury or colored alcohol thermometer, which is a narrow sealed glass tube containing that liquid. But why mercury or colored alcohol is chosen? Because their volume expand drastically or contract drastically if the temperature changes. So we know, and we're going to learn later on, that many materials or substances will change their volume as the temperature changes. Now, when a thermometer is placed in a liquid or gas, the particles of that substance bump into the glass of the thermometer. And let's get an example. So if there's a low temperature around this thermometer, that means that the amount of kinetic energy of their particles, liquid or gas, that they possess is smaller compared to the amount of kinetic energy of the particles of the glass. So when they bounce back and forth with the glass of the thermometer, they will exchange that amount of kinetic energy. So that extra amount of kinetic energy that the glass particles possess compared to liquid or gas will be transferred to those molecules of air or liquid. So that will result to a slow down or decrease of that kinetic energy of those particles. But remember, those particles are in contact with a liquid as well. So that means in a contact, they are going to exchange that difference in kinetic energy. So that means that will make that liquid to lose some kinetic energy to glass, and glass is going to lose that kinetic energy to environment, air or gas or liquid. So that means that by decreasing the temperature, mercury or colored alcohol will decrease the volume. So that's why you'll see a reading on a thermometer to be lower, because the volume will decrease. If you place the same thermometer in a warmer environment, that means that those molecules of gas or liquid possess more kinetic energy, moving rapidly than normal. So when they bounce with the glass, they will exchange that kinetic energy. They'll give away some of their energy to the particles of glass, making the particle of glass to be moving rapidly, more rapidly, possessing more kinetic energy and feeling warmer. And that transfer of energy, kinetic energy, is going to happen in a contact with liquid as well. So that extra energy is going to be transferred or balanced into a liquid as well. As a liquid will have more kinetic energy, the particles of the liquid is going to rapidly, molecules of the liquid is going to rapidly move, and it's going to move away from each other. So that means that the volume is going to increase, filling up that narrow sealed glass tube. So it's going to show us a bigger reading. So we know now that this environment around this thermometer is warmer because that liquid is expanded. That's how you read a thermometer. There are two popular scales to measure temperature, and one is for physics only. The most widely used scale is a Celsius scale. This is named after Anders Celsius, a Swedish scientist who based the scale on the temperature at which water boils and freezes. So the pure water freezes at 0, and we can just make a mark here at the 0 degrees Celsius, and boils at 100. And then we can split this in 100 pieces, in 100 equally spaced lines. So a difference between two equally lines is 1 degree. And we can label the rest, a negative part of it. Now the second one is a Fahrenheit scale. Was invented by Daniel Gabriel Fahrenheit, and it's based on a temperature at which a brine or salt water solution freezes and boils. Now to compare both of those, so we know the pure water freezes at 32 degree Fahrenheit. In a degree Celsius is a 0, in a Fahrenheit is 32 degree Fahrenheit. And it boils in degrees Celsius is 100, and in Fahrenheit is 212. So in this relationship between boil and freezing, we can have a formula that converts degree Celsius into a Fahrenheit and Fahrenheit into a degree Celsius. There is another scale that is used to measure temperature. There's a Kelvin scale, which is based on a total amount of thermal energy that substance possesses. The Kelvin scale is invented by William Thomson or Lord Kelvin. Kelvin scale is always positive number. So even it has a 0 or a lowest Kelvin point is called an absolute 0, which is a minus 273.15 degrees Celsius, is the temperature at which the particles of substance have slowed down so much they hardly can move at all. So the particles cannot move. We can call it a dead particle. That doesn't exist. The absolute 0 does not exist, is not reachable. The standard unit for temperature is Kelvin. So in order to convert from Kelvin scale to a Celsius scale or vice versa, we can use the following equation where a Tc is temperature in degrees Celsius and Tk is temperature in Kelvin. Remember, that's a very interesting thing to mention, that we can use degree for degree Celsius and degree Fahrenheit, but we cannot use degree for Kelvin. We just say simply Kelvin. So temperature in Kelvin is equal to temperature in degrees Celsius plus 273, or temperature in degrees Celsius is equal temperature in Kelvin minus 273. It's very interesting to see those formulas to convert degrees Celsius into Kelvin and from Kelvin to degrees Celsius. However, this is interesting to see those temperatures side by side. So you know the freezing point of the water is 0 degrees Celsius, but you can express that freezing point into a 273.15 Kelvin. And boiling point for water is 100 degrees Celsius, but you can say the water can boil at 373.15 Kelvin. If you see that Kelvin is all positive, degrees Celsius thermometer is negative, 0, and positive. Now, what about that 0 Kelvin? 0 Kelvin means that the pressure is going to drop drastically, and it is going to reach the point there is no pressure at all because those particles are not moving at all. So no particle is going to hit the wall of the container. See, particles of a gas, for example, in a container, usually they hit the wall, bounce back and forth from the wall of the container. However, in that situation where there's no kinetic energy, no moving, that means that those particles are going to fall down to the bottom of the container because of the gravity. So there's no moving or no bouncing at the wall. So the pressure is going to show 0 pressure. That means that is a dead particles, dead matter, which does not exist. Let's do some practice. Converting Celsius to Kelvin scale. Ethyl alcohol boils at temperature of 78.3 degrees Celsius. What is this temperature in Kelvin? So what is given is temperature in degrees Celsius, 78.3 degrees Celsius, and temperature in Kelvin is required. So we can use the temperature conversion formula. Temperature in Kelvin is equal to temperature in degrees Celsius plus 273. That will give you 351 Kelvin. So we can say ethyl alcohol boils at a 351 Kelvin. It freezes at 159 Kelvin. So alcohol freezes at 159 Kelvin. What is this temperature in degrees Celsius? So we can actually use the other formula, converting the Kelvin into a degrees Celsius by subtracting 273, and we get negative 114 degrees Celsius. There is a connection between thermal energy, temperature, and physical state. Substances increase in temperature or warm up when they absorb thermal energy, and they decrease in temperature or cool down when they release thermal energy. When a thermal energy is absorbed by a solid substance, the solid eventually melts into a liquid. And the temperature at which a solid melts into liquid, we call it as a melting point. That is equal to a freezing point for a given substance. So a freezing point is a temperature at which a liquid changes to a solid, equal to a melting point for a given substance. We can say the same thing for evaporating and condensation point. When evaporating liquid turns into gas, and condensation point is when gas turns into a liquid. So we reach at the end of this lesson. Here is a summary. The total amount of the kinetic and potential energy possessed by particles of the substance is called thermal energy. So thermal energy is about total kinetic and potential, both. Temperature is a measure of average kinetic energy, not kinetic energy, but average kinetic energy, because it is impossible to calculate kinetic energy of the particle, of each individual particle. The kinetic molecular theory states as particles of matter gain kinetic energy, they move faster, and the temperature of the substance increase. So temperature is in a direct proportional with kinetic energy of the particles. As particles of matter loses kinetic energy, they move more slowly and the temperature decreases. Temperature can be measured by using 3 scales. 2 scales are popular and we use degree. So degree Celsius scale, degree Fahrenheit scale, and Kelvin scale, which is used only in physics and is a standard unit for temperature in physics. Remember, you can use Kelvin, not degree Kelvin. And that's about it. Have a good one.